at a radius of, well, let's make it big. 4 meters. Solid disc or cylinder, whichever way you like. Is this the type thing you're thinking about?
Yeah.
All right. What's the first step?
Force diagram.
Yes. So I got 5, I got 3, I got a pulley, I got a rope. Because we are dealing with friction between the pulley and the rope, we are going to treat it like 2 different ropes. Step 2, acceleration. Direction of?
I'm presuming the box 5 will go to the right,
Okay.
and then box 3 will just fall down. Well, acceleration going down.
If it's going to accelerate, I don't think it's going to go the other way. All right, so that direction, that's the direction of acceleration here. That's the direction of acceleration here. What about the pulley?
It's going on a. How would you describe that? I know it's gonna go this way.
Yeah, how do you describe the direction of that angular acceleration? Linear acceleration of this, the pulley's not, the center of the pulley is not moving. So I don't have to worry about A just yet. We do have an angular acceleration there. If it's going to, if the angular acceleration, yep.
Oh.
So what's the direction, Pratika?
Into the board.
Okay.
Oh, we skipped the force diagram. That's where we were. Then you came up with that question about acceleration. So, force diagram.
Tension is acting on box 5 and the string, and it goes the same for box 3 and the string. There's also tension between the pulley and the strings.
I'm still considering the mass of the string to be irrelevant,
Are we
and it's not stretching.
Are we considering the normal force pulling up on the pulley? Would that affect our calculations at all?
It's not, because ultimately we're dealing with rotational motion here, and whatever's holding the pulley up, we assume is exerting no torque.
Okay.
If it's being balanced here, there is a normal force here, y sub p, and a normal force acting back. All right, so we got tensions and one normal force pair.
Normal force acting up off of the 5 kilogram box. And then off the ground below it. Is there friction?
That's the normal force acting on the pulley from there. I've separated the pulley from, well, I have to separate the pulley. The pulley's a separate object from the ground. And there would be some normal force acting on the rope here, but I'm considering the rope is basically attached to the pulley at this point, so the part of the rope touching the pulley, I couldn't consider part of the pulley. So any force between the rope and pulley would be an internal force. It would not exert any torque, so ultimately, doesn't change anything. Sorry, you were saying?
Well, firstly, how's the acceleration to the right if the 5 is heavier?
Which way? If it starts at rest,
Yeah.
it has only one choice but to go that way. If this is level, there's nothing forcing it in that direction.
Right.
And you're saying there's no friction between 5 and the ground, right?
Where's your friction?
I was thinking no, but
Okay.
we can throw it in if you want.
No, thank you.
Okay.
Would that make the calculations a lot harder, or will it just not really do anything?
Not you're adding another term. Harder, if you're really, really weak in math, then yes, but if not, it adds, 30 seconds to the problem.
We're not in static equilibrium, right?
Yeah,
Okay.
I'm assuming not. Especially if there's no friction there.
We acting down on the 5 kilogram and the 3 kilogram masses, but would it be acting straight down from the center for the pulley?
Yeah.
Yeah. But that will not be used for that calculation, right? Because
Why?
it's just in the axle. We're not concerned about the axle. We're concerned about the pulley rotating.
And it exerts no torque. 55, we got W3, assume that's all part of the ground. So that's, all right, then we do acceleration. Coordinate system.
For the, I'll start off with the pulley. I'm saying
Okay.
it's, so, I wanna get this right. And then, so it's FT3 minus FT5?
Wait.
Or,
Coordinate system.
oh, coordinate system, sorry. I got too jumpy. I'll be just the same one as the acceleration.
Go into the board.
Yeah.
Whatever letter you want to use, wait, into the board.
Yeah.
Okay.
What letter for what?
For the labeling, I'm labeling it the K-hat.
Oh,
The
okay.
K direction. K-hat direction. What about the 5?
What about the what?
Okay, so I hat, which way did you say J-hat?
J.
J-hat down? And then 3?
Down.
All right.
Now, is it FT3 minus FT5?
Do we have to decompose anything?
No.
All right, equations of motion. You wanna do, so we got the K-hat form, we have K-hat, J5 hat, I5 hat, and J3 hat. So we got 3 equations. It's not gonna be tension 5 minus tension 3,
No, I said 3 minus 5. Is that
or
right?
even 3 minus 5.
Really?
Because those forces are not causing acceleration, are not, we're plugging into, because we're dealing with rotation,
Yeah.
we're not plugging into F equals ma. We're plugging into tau equals ma. Or sorry, tau equals IA, alpha.
So is it the torque of FT3 minus torque of FT5?
So torque of 3 minus torque of 5
So I was close.
equals,
In moment of inertia times angular acceleration.
okay,
And
1 down.
For J hat of 5, it's W5 minus Y5 is equal to M5A. Oh no, 0.
Yeah, I hope it's not accelerating up or down.
I hope so too.
All right, next.
It's FT. no,
FT5 equals M5A.
Okay,
W3 minus FT3 equals M3A.
And those A's are the same. If the rope is not stretching, then they will accelerate at the same rate. As well as that acceleration would be the acceleration of a point on the outer edge of the tangential acceleration of a point on the outer edge of the pulley. All right, what's next?
Substitution.
All right,
I think for the torque, it's going to be moment arm times the tensions so that we can cancel out the R's.
all right, so R times FT3 minus R times FT5. Now, if you want to get into R cross F, recognize that because the way we've defined our positive direction here, FT3 is causing it to rotate about that point in the positive direction. We've already taken the direction into account. Equals,
MR squared, wait, is that a solid disk?
so yeah,
So that's a 1/2 MR squared.
M pulley, R pulley squared.
And then, should we decompose the angular acceleration already?
It is angular acceleration. What form, you want to go ahead and do that substitution?
A divided by R. Because,
And that R would be the same R. All those R's are the same.
so they cancel out.
Now, the Goldberg test, I think that you had a situation where the R's did not cancel out,
Really?
because you had torque was being applied to a larger wheel, but then you had a pulley system on a smaller wheel, or vice versa, one or the other. Can't quite remember.
I am confused about how all of them are
All the R's cancel out?
canceling out.
All right.
Because one is R squared. Sorry.
All right, so we have, this is the radius, this is R cross F of this force right here. R is the radius of the pulley. So this would be radius of pulley times, not torque there, FT3. For torque 5, that's coming from a force that is acting the distance R away from the axis of rotation. So minus R FT5. Both those are the radius, each is the radius of the pulley. Equals the moment of inertia, which is 1/2 times the mass of the pulley times the radius of the pulley squared times alpha. If I'm looking at a point here, relating the angular acceleration with the tangential acceleration, again, it's the distance away from the center that matters, which is R. So this would be A over R.
I guess my question is, when R is canceling out, why is R squared not just left as R on that side?
I've got R squared here, those R's are the same. Even though I put a subscript P there, this is really radius of the pulley, radius of the pulley, radius of the pulley.
I feel very stupid right now. I think,
I'm missing the question.
oh, okay, I get it now. Okay, so the R squared on the bottom cancels out one of the R's in the 1/2 MR squared. And
Yes.
then because there's R, okay, sorry, I just need my brain to do catch up.
All right. You got it.
Thank
You got it.
you.
Why are we ignoring the normal force of the pulley?
Torque, in order for there to be torque, the normal force needs to be, the force cannot be at the axis of rotation. If the force is pointing at the axis of rotation, you're not gonna rotate it. If I went to the door and I pushed on the door on the end, so if this were a door here and I wanted to rotate it about here, if I push this way or pull that way, I'm not gonna get it to rotate at all. If I wanted it to rotate about here, I have to pushed so that the force is not directed at this. In the case of the pulley, I have this normal force here that's coming basically between the axle and whatever, and the pulley, or the axle, or whatever's holding the axle up. That force is going right through the axis of rotation. So that exerts no torque. From a mathematical point of view, torque is equal to R cross F. This is equal to 0 if the moment arm is 0, the force is 0, or the moment arm is perpendicular to the force. In this particular case, the moment arm would be 0. Because the moment arm is a force, is a vector from, parallel. In this case right here, the moment arm is 0 because the force is acting at that point right there,
In the middle.
in the middle. Or if you want to consider a normal force, somewhere else, the normal force is going to be pointing away from the center. So even if I had a normal force here, so if I had a normal force pointing that way, well, my moment arm would be a vector like that. That'd be R, that would be F. They're parallel in that case.
Okay.
Okay.
Yes?
If the radius were not all the same, you have to go through the R times F sine theta and all those stuff.
Not necessarily bringing in the sine theta, but possibly. In the Rube Goldberg tests, you still weren't bringing in the sine theta.
Is it the same for the weight as well?
Yes.
Because it's parallel or because it's to the center?
Yes. Or, yeah, that works. Is that good enough, or I can go through another way of looking at it?
I would like to listen to that as well.
All right. There's a gravitational pull in every part of this. The gravitational part here, gravitational pull here, and so forth, in which case R is not 0, this has a torque, this has a torque. But because of symmetry, for every particle here with a gravitational force downwards, with a movement arm like that, I got another one over here. So all those torques would cancel out.
Symmetry.
And that's the reasoning for weight not being used for the torque.
Yes.
Yeah.
Is that the same for the ladder problem? Well, hold on. We considered weight on the ladder.
It turns out that if you can, unless you want to get into, let's say I got a beam here being supported by 2 logs. If you are looking at how this beam is going to sag, because there's a gravitational pull on everything, you can't get away with it. So future civil engineers, at some point, you're gonna have to take into account the fact that there is weight distributed throughout. If you are not considering that, then it turns out you can always treat it as, I have weight acting at the center of mass, and treat it like that. So if I had a seesaw, I could look at this as, I have my center of mass here, I got my pivot point there, there's my R. And I could figure out the angular acceleration. So that's the center of mass. I could also look at it as, if I have the same beam, where my center of mass is here, I can treat it as 2 objects. This half over here has a center of mass there, trying to create torque in that direction. This has a center of mass over here, so this half has a center of mass, creating a torque point in the opposite direction.
And then just add them together and look for the net torque.
Yeah, and you would get the exact same result as if you had just taken the center of mass of the beam to start with that moment right there.
Okay. It just really depends on what's given to us in the question.
Yeah, what's given to you, and of course, which way your mind is working at the moment you need to use it.
All right.
Okay, so we have this one right here. Sorry, any other questions before we move on? This equation, since there's no friction, this equation's not gonna do anything, but if you had to, y5 is equal to m5g. This one, ft5 is equal to m5a, and then m3g minus ft3 equals m3a. So that equation not gonna matter. Here, we canceled out the r's, as has already been referenced. And so that equation becomes ft3 minus ft5 equals 1/2 mass of the pulley times A.
And then you subtract, you add them all together.
Hey, the ft3's cancel out. The ft5's cancel out. And I have m3g, which is basically the force driving the whole system, is the weight of mass 3 that's dangling there, is equal to mass 5 times A plus mass 3 times A plus 1/2 times the mass of the pulley. If we were dealing with an ideal pulley, an ideal rope, and there's no friction acting between them, then that term would disappear. And it's the classic, that's the total force acting on it, that's the mass that's being moved, and the acceleration. But because we do have the pulley turning, and we're taking that into account, this is the extra factor that gets thrown in. And then, Mike and John. Is that,
Yeah.
okay.
Do you mind also trying, like, how do we find the angular speed on like